welcome to this problem walkthrough. Today, we'll explore an interesting challenge, problem number 943, titled Find the Shortest Superstring. We'll break it down step by step, discuss possible approaches, and focus on building an efficient solution. Let's dive in. In this problem, we are given a list of strings called words, and our task is to find the shortest string, known as a superstring, that contains every string in words as a substring. A superstring is simply a larger string that includes each word from the list as a part of it in some position. The goal is to minimize the length of this superstring. If there are multiple shortest superstrings with the same length, we can return any one of them. For the input and output format, the input is a list of strings where the number of strings can range from 1 to 12, and each string consists of lowercase English letters. The length of each string can be up to 20 characters. The output is a single string which represents the shortest superstring that satisfies these conditions. To better understand, let's look at the first example. If the input list of words is Alex loves LeetCode, one possible shortest superstring is Alex loves LeetCode. This string contains all three input words. Specifically, Alex appears as a substring starting at index 0, love starts at index 4, and LeetCode starts at index 9. Importantly, this superstring is the shortest possible string that satisfies the condition of including all the input words as substrings. Even though there might be other superstrings, this one achieves the minimum length. Now, let's look at another example with more overlap between the words. If the input list is kak, tagged, tka, adkak, one possible shortest superstring is tagged katkak. Here, the overlaps between the strings allow us to combine them more efficiently. For instance, kak starts at index 0, and tagged overlaps with it starting at index 1. Similarly, tka starts at index 0, tka starts at index 5, and adkak begins at index 7. This overlap minimizes the total length of the resulting string, making it the shortest valid superstring for this input. Let's discuss the constraints and edge cases. The constraints ensure that the problem size is manageable, with up to 12 words in the input and each word being relatively short, up to 20 characters. This allows us to consider combinatorial approaches to solve the problem. For edge cases, when there's only one string in the input, the result is simply that string. If all the strings are identical, the result is just one of those strings. If the strings have no overlap, the result is their concatenation in any order. Finally, when there are multiple overlaps between strings, any valid superstring of the minimum length is acceptable as the solution. For example, with a byte BC, CD, both ABCD and ABC are valid outputs depending on how the overlaps are resolved. To tackle the problem of finding the shortest superstring, the brute force approach offers a straightforward starting point. Here, the idea is to generate all possible permutations of the strings in the input array and construct a superstring for each permutation by overlapping adjacent strings as much as possible. Among these, the solution with the shortest length is chosen. Now, while this approach is conceptually simple, it quickly becomes computationally infeasible due to its factorial time complexity, which arises from the need to evaluate all permutations. Additionally, calculating overlaps between strings adds an extra layer of complexity, making it impractical for larger inputs. This method works well for understanding the problem at a basic level but isn't viable for real-world use when the number of strings grows beyond a small number due to its exponential growth in both time and space requirements. A more sophisticated and efficient approach uses dynamic programming combined with bit masking. This strategy treats the problem as finding the shortest path in a weighted graph, where each string is represented as a node, and the edge weights correspond to the overlap lengths between strings. The key is to use dynamic programming to systematically explore all possible paths while minimizing the overall length. To achieve this, we pre-compute the overlaps between all pairs of strings, which takes n² time. Then, we use a dp state represented as dp mask I, where the bit mask keeps track of which strings have been used, and I is the last string in the current path. The transitions involve selecting the string that minimizes the cost of extending the superstring. Finally, after the dp table is filled, we reconstruct the optimal solution. While this method is computationally more efficient than brute force, its exponential scaling with respect to the number of strings still makes it suitable only for small to medium-sized inputs. This dynamic programming approach, while optimal, does have its limitations for very large inputs due to the exponential scaling caused by the 2 to the power of n factor. For cases where speed is prioritized over exact optimality, a greedy approach can be considered. In this method, we iteratively merge the two strings with the maximum overlap until only one string remains. This heuristic significantly reduces the computation time compared to dynamic programming, with a time complexity of n²*k. However, the trade-off is that the solution may not always be the shortest superstring, as the greedy approach lacks the global optimization that dynamic programming provides. It's faster and simpler but can lead to suboptimal results, especially in cases where early merging decisions negatively affect the overall outcome. Among the three approaches, dynamic programming with bit masking stands out as the most suitable for this problem. Its systematic exploration of all possible paths ensures that the shortest superstring is guaranteed, making it the optimal solution for small to medium-sized inputs. Although its complexity grows exponentially with the number of strings, the use of overlap precomputation and bit masking helps reduce the problem size and makes it computationally manageable for inputs where n is less than or equal to 12. Compared to brute force, the DP approach drastically cuts down the search space, and while it is slower than the greedy method, it ensures the desired optimality. In conclusion, dynamic programming with bit masking is chosen because it strikes the right balance between computational feasibility and guaranteed correctness, addressing the problem's requirements effectively. The shortest superstring problem asks us to find the smallest string that contains all given strings in an array as substrings. To solve this, we start with a brute force approach that explores every possible way to order the strings. The first step in the algorithm is to generate all possible permutations of the input array. This is crucial because the order in which we concatenate the strings significantly affects the final length of the superstring. To achieve this, we can use a backtracking algorithm or a built-in library function like itertools.permutations in Python. For example, if the input array is ABC, BC, CDE, we generate permutations such as ABC, BC, CDE, and ABC, CDE, BC, among others. These permutations will help us test all possible combinations and identify the optimal superstring. Once we have the permutations, the next step is to calculate the overlap between adjacent strings in each permutation. Minimizing the length of the superstring requires merging overlapping substrings wherever possible. To do this, we compute the maximum overlap between two strings, where the suffix of the first string matches the prefix of the second. For instance, if we have S1 equals ABC and S2 equals BCD, the overlap is 2 due to the matching substring BC. After identifying the overlap, we merge the strings by appending the non-overlapping part of the second string to the first. In this example, merging ABC and BCD results in ABCD. Following this, we construct a superstring for each permutation by iteratively merging strings using the overlap calculation. For the permutation ABC, BC, CDE, we first merge ABC and BC to get ABC, then merge ABC with CDE to form the superstring ABCD. After constructing superstrings for all permutations, the next step is to compare their lengths. The goal is to identify the shortest superstring, which represents the optimal solution. To do this, we track the minimum length and the corresponding superstring as we evaluate each permutation. Once all permutations have been processed, we return the shortest superstring as the solution to the problem. While this brute force approach guarantees the optimal solution, it comes with a high computational cost due to its factorial time complexity. This makes it impractical for large inputs, but it provides a clear and thorough way to approach the problem. Key insights include the importance of calculating overlaps greedily to minimize the superstring length and handling edge cases like identical strings, no overlaps, or an empty input array effectively. To implement this approach efficiently, we rely on specific data structures. A list is used to store all permutations of the input strings, and strings are used to construct the superstring for each permutation. The time complexity of the algorithm is dominated by three components: generating all permutations, which takes O(n), calculating overlaps for each pair of strings, which takes O(n²), and merging strings to form superstrings, which takes O(n*)(n). The total time complexity is therefore O(n*)(n). The space complexity is O(n), primarily for storing intermediate results.
To improve efficiency, we can use optimizations like memoization to store overlap calculations and avoid redundant work.
Additionally, pruning techniques can help discard permutations early if their partial superstring exceeds the current minimum length. These strategies, while not reducing the factorial time complexity, can significantly speed up the computation in practice. Here, we start by importing the permutations function from the itertools module, which will allow us to generate all possible orderings of the given list of words. Then, we define a solution class with a method called shortest superstring. Inside this method, we first define a helper function named overlap. This function calculates the maximum overlap between two strings, S1 and S2. It does so by checking the largest suffix of S1 that matches the prefix of S2, iterating through all possible overlap lengths.
The maximum overlap is then returned.
Next, we define another helper function called combine, which uses the overlap function to merge two strings. It combines S1 and S2 by appending the non-overlapping portion of S2 to the end of S1. After defining these helper functions, we initialize two variables, min_superstring to none and min_length to infinity. These will help us track the shortest superstring and its length during the computation. Finally, we use the permutations function to generate all possible orders of the input list of words. For each permutation, we initialize the current superstring as the first word in the permutation and iteratively combine it with the subsequent words using the combine function. Once we have constructed the superstring for a particular permutation, we check its length. If the length of the current superstring is less than the minimum length found so far, we update min_superstring to the current superstring and min_length to its length. This ensures that by the end of this process, we will have the shortest superstring among all possible orderings of the input words. Finally, we return min_superstring as the result. This brute force approach guarantees that we consider every possible way of combining the words, ensuring the solution is correct. However, because it generates all permutations, its computational complexity can be high for larger input sizes, making it less efficient for very large datasets. Nevertheless, this implementation provides a clear and straightforward way to solve the problem by exhaustively exploring all possible combinations. Here, we start by importing the necessary libraries and defining the solution class. The first method, calculateOverlap, determines the maximum overlap between two strings by comparing suffixes of the first string with prefixes of the second string. We iterate over possible overlap lengths, updating the max overlap variable whenever a match is found. This forms the basis for combining strings efficiently later. Next, the combine_strings method uses the calculated overlap to merge two strings, appending only the non-overlapping portion of the second string to the first. Finally, we begin the shortest superstring method, which initializes variables and sets up the structure for finding the minimum length superstring for the given array of words. To compute the shortest superstring, we first initialize min_length to track the smallest superstring length found so far and create a list to store all permutations of the input words. Using the generate permutations helper method, we populate the permutations list with every possible order of the words. For each permutation, we start with the first word and iteratively combine it with the next word in the sequence using the combine_strings method. By the end of each permutation, we check if the resulting superstring is shorter than the current minimum length. If it is, we update both the shortest superstring and min_length variables. This approach ensures that we evaluate all possible arrangements of the words to find the optimal solution. The generate permutations method is implemented here as a recursive function that generates all permutations of the input array. When we reach the base case, where the start index equals the array's length, the current permutation is added to the result list. To explore all permutations, we use a loop to swap the current start element with each subsequent element, recursively generating permutations for the rest of the array. After processing each recursive call, we swap the elements back to restore the original order, ensuring no side effects for future iterations. Lastly, the swap method is a simple utility function that exchanges two elements in the array, facilitating the reordering required for permutation generation. To solve the problem of finding the shortest superstring, we begin by defining two key functions, overlap and combine. The overlap, S1 with S2, function determines the maximum length of the overlap between the suffix of the first string and the prefix of the second string.
For example, if S1 ends with CA and S2 begins with CA, the overlap is 2.
The combine S1-S2 function uses this overlap to merge the two strings into one, ensuring no redundant characters. Once these functions are defined, we generate all possible permutations of the input list of words. For instance, with the input words equals cat, tagged, ta, tka, adcac, one of the permutations could be cat, tagged, ta, tka, adcac. For each permutation, we compute the combined superstring by sequentially merging words based on their overlaps. Starting with the permutation cat, tagged, ta, tka, adcac, we initialize current_superstring as the first word, which is cat. Next, we combine cat with tagged. Here, the overlap between these strings is 2, as CA at the end of cat matches CA at the start of tagged.
The combined result is catgagged.
We then merge this result with the next word, cha. The overlap in this case is 1, as G matches, giving the combined result catgaagta.
Continuing, we combine this with ta, where the overlap is 2, resulting in catgaagtatka. Finally, merging this with adcac with an overlap of 3 yields the final superstring catgaagtatcatcat with a length of 23. This process is repeated for all possible permutations of the input words. After evaluating all permutations, the shortest superstring is identified. For this example, the shortest superstring is tagcatcac, with a length of 16. Now, let's consider another example with the input words equals ABC, BCD, CDE. For the first permutation, ABC, BCD, CDE, we start with current_superstring equals ABC. Combining ABC with BCD gives an overlap of 2, as BC matches, resulting in the superstring ABCD. Next, combining ABCD with CDE, we find another overlap of 2, where CD matches, leading to the final superstring ABCDE with a length of 5. Repeating this process for the other permutations, such as BCD, ABC, CDE, and CD, ABC, BCD, we see that all produce the same superstring ABCDE with the same length of 5. Thus, for this example, the shortest superstring is ABCDE. Finally, consider the input words equals A-B-B-A. For the permutation A-B-B-A, we begin with current_superstring equals A. Combining A with AB gives an overlap of 1, where A matches, resulting in the superstring AB. Then, combining AB with BA, we find another overlap of 1, where B matches, producing the superstring ABA with a length of 3. Checking other permutations, such as AB-A, we again get ABA as the result. However, for the permutation BA-AB, the superstring becomes BAB, also with a length of 3. Among all results, the shortest superstring is the one with the minimal length. In this case, both ABA and BAB are valid solutions with the same minimal length of 3. Here, we analyze the time complexity of the solution. The first step involves generating all permutations of the n input words, which takes n time because there are n possible orderings. Once the permutations are generated, we then need to combine the words in each permutation to form a superstring. For this, we use the overlap function to calculate the overlap between two words. The overlap function iterates over the characters of the two words, up to the length of the shorter word. Assuming the maximum length of any word is L, the overlap function takes L in the worst case. Combining two words, therefore, also takes L time. Since there are n words to combine in each permutation, the total time for combining words in one permutation becomes n*L. Now, since there are n permutations, and combining words in one permutation takes n*L time, the overall time complexity for iterating over all permutations is n*L. Next, let's analyze the space complexity. Generating all permutations involves temporarily storing n permutations in memory. Each permutation contains n strings, so the total memory required for storing permutations is n*N. Additionally, during the combination process, temporary strings are created. In the worst case, the combined string can grow to the sum of all word lengths, which is n*L. Together, these factors contribute to the overall space complexity. The final aspect of space complexity comes from the output string, which is the shortest superstring returned as the result.
its length is at most O, n asterisk L. Combining all these factors, the overall space complexity is O, n asterisk n plus n asterisk L. However, for large values of n, the factorial term n dominates, so the space complexity simplifies to approximately O, n asterisk n. Lastly, let's consider the best, average, and worst-case scenarios. In all cases, the algorithm generates all n permutations and processes each one, meaning the time complexity remains O, n asterisk n asterisk L, regardless of overlaps. This is because the solution does not include any optimization to terminate early or avoid unnecessary calculations. To put this into perspective, this algorithm is fundamentally brute force, as it tests all possible arrangements of the input words to find the shortest superstring. While this guarantees correctness, it is computationally expensive. In contrast, more efficient approaches, such as dynamic programming with bitmasks, like the Heldkarp algorithm, can significantly reduce the time complexity to O, n squared times 2 to the power of n plus n times L. The space usage in such optimized approaches is also much lower, typically O, n asterisk 2 to the power of n. Mathematically, the factorial time complexity arises because generating permutations is inherently O, n. And combining words across one permutation involves n operations, each taking O, L, resulting in a total time complexity of O, n asterisk n asterisk L. Space complexity, dominated by storing all permutations, remains approximately O, n asterisk n. When tackling this problem, there are some common mistakes that can trip up even experienced coders. First, incorrect overlap calculation is a frequent issue. Remember, the goal is to compute the maximal overlap between two strings, as this is key to minimizing the length of the resulting superstring. Overlooking partial overlaps or missing cases where there's no overlap can completely derail the logic. Next, relying on brute force without optimization is another pitfall. While generating all permutations of strings might seem straightforward, it's computationally prohibitive as the number of strings grows. The time complexity of O, n makes this approach impractical for anything but the smallest inputs. Lastly, ignoring edge cases is a critical mistake. Scenarios like empty strings, identical strings, or strings with no overlap need special handling. Failing to address these can lead to runtime errors or incorrect results, so always account for these possibilities in your solution. Another mistake to watch out for is making suboptimal greedy choices. It might be tempting to select overlaps based purely on immediate gains, but this can lead to a longer superstring down the line, as future combinations are not considered. Similarly, not accounting for the order of input strings can cause problems. The sequence in which strings are processed directly impacts the overlaps and the resulting superstring length, so it's crucial to evaluate different orders rather than assuming one is sufficient. Now, for interview preparation, focus on how you optimize overlap calculations. Be ready to explain your approach, whether it's through dynamic programming or bitmasking, as these techniques demonstrate your ability to tackle complex problems. Discuss the trade-offs between brute force simplicity and optimized approaches like DP or graph-based methods. Make sure to address edge cases early to impress interviewers with your thoroughness. Finally, always analyze the time complexity of your solution, whether it's O, n, for brute force or O, n asterisk 2 to the power of n, for a more advanced DP approach. Being clear about this will show your depth of understanding. To deepen your understanding of this problem, it's helpful to explore related challenges. For instance, LeetCode 943 itself is a great starting point, but you might also look at problems like k-empty slots or reconstruct itinerary, which involve sequencing and optimization. Similarly, concatenated words offers another perspective on string manipulation. Now, in terms of alternative approaches, dynamic programming with bitmasking is a powerful method. Here, you maintain a DP array where each state represents the shortest superstring ending with a specific string and covering a subset of strings. While this approach is more efficient than brute force, it does require careful implementation to track masks and overlaps accurately. Another option is the graph-based approach, where overlaps are treated as edges in a weighted graph. Solving this via a traveling salesman problem heuristic can be elegant and scalable, but keep in mind that TSP approximations may not always yield the shortest superstring. A simpler alternative is the pure greedy approach, where you repeatedly merge the two strings with the maximum overlap until only one string remains. This method is faster and easier to implement, making it a good choice for time-constrained interviews. However, it's important to note that it doesn't guarantee the optimal result, as greedy choices can miss better solutions that require foresight. This approach can still be useful in scenarios where an approximate solution is acceptable and speed is prioritized over precision. To wrap up, we reviewed the find the shortest superstring problem, summarized the brute force approach, and highlighted key takeaways about superstrings and optimization.
Thank you for watching.
If you found this helpful, be sure to like, share, and subscribe for more coding tutorials.
Until next time, happy coding! That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!